the same length. So make sure you understand that difference, that inside the boundary layer, you always have rotational flow. Outside of the boundary layer, you do not. So let's say, for example, let's have you guys help me out here. So my lens, so if we have a pipe flow and the pipe flow is fully developed, do we have fully rotational flow?
Home or no?
My lens.
Like for 6 or 7.
And on my lens.
Yeah.
Philip, so in a pipe flow, it's in terms of no flow, fully developed, do we have rotational flow?
Just be Aaron.
No, Philip. Okay. All right, maybe let me see.
Yes.
Maybe I'll let you guys. Maybe easier if you guys just participate. And it seems like some folks are missing today. So if you want to go ahead, someone.
Sorry, I just got here. Signed in a second late. I missed the question.
So Philip, if you have, let's say we said, hey, if we have a boundary layer, we always have rotational flow there. Outside of the boundary layer,
like he said,
no rotational flow. Why? Because there's no velocity gradients. What about in a pipe flow where the flow is fully developed? Do we have rotational or irrotational flow?
You just smoke.
It would be irrotational.
So let's look very quick at pipe flow. Let me see if I can draw something here. It's not letting me get.
Now, Kevin, you just translate to Val.
For whatever reason, it's not letting me get the pen to draw on the screen. So think about it. If you look at a pipe flow, is the velocity uniform throughout, or is there some sort of profile where the velocity is changing with respect?
There would be a profile, a gradient.
Okay. So if there it is, if we look at this equation right here for angular velocity, this is telling us there's velocity gradient. So if that's finite, what does that mean in terms of the angular velocity?
That there must be an angular velocity.
Right. So it's rotational.
Okay.
Okay. So everyone, please make sure you understand that if you have a velocity gradient, the flow is going to be rotational. If you're at the beginning of the flow in the pipe and it's all fully, it's uniform, where all your vectors are the same length, regardless of position, you have irrotational flow. But if you're in a boundary layer or the flow has become fully developed where you have a velocity profile, the flow is rotational. All right. So then we also talked about linear deformation, where we can calculate it with the following equation right here, where you see the flow is deforming, where it will be lengthening, or if you have angular deformation, which will be your will be like a shear strain. So here you have a normal strain, shear strain, and then up here we have the angular velocity, and that's how you can say, yes, we have rotational or irrotational flow. All right. And these are very important. Especially when you're looking at boundary layers and so on, it makes the
shouldn't you know
problem,
the hours by now, though?
It helps you simplify significantly if you're in the boundary layer and outside. All right. So so we already went through flow that is rotational, and then we determine if it's rotational or not simply by calculating this these velocity gradients right here, and so that's how we would determine that. So okay. Let's go now to, and then just quick point I want to make, angular velocity and vorticity, they're related. That one is just going to be twice the amount of the other. So that's how those two. So you could either choose the angular velocity or vorticity equation, and you can show that the flow is rotational. So then from there, we quickly went on to conservation of mass. And then in conservation of mass, we stated, hey, we're going to apply it to very small fluid packet, really, really, really small. And when we apply our integral form of the conservation of mass, we end up with the following differential equation, a partial differential equation. And then we have this term with respect to time. And then the other terms are with respect to space. And we said, hey, if our flow is incompressible, so it means that density is not changing. So it means it's not changing if I'm up at 0.1 and then I move over to 0.2, if the density is still the same, then that means I have incompressible flow. So when we have that, when the flow field is incompressible, we have that the density is constant. And then when that is constant, then it means that the divergence of the velocity here, this product, dot product right here, is just equal to 0. So, and we talked about, hey, what about if I have some flow field that looks something like this? how can I find that it is indeed incompressible? And let's go back to Julius. Do you remember how, if we had this velocity vector right here, we want to say, hey, is this compressible or not? How could we do that? Do you remember, Julius, by any chance?
If the density does not change.
If it's incompressible, you're given a vector field that looks something like this. We have this vector, and you're asked, hey, is this incompressible or compressible flow?
If V remains constant.
So do you remember what we talked about in this lecture? We said, so this is the condition that we're giving. This is for incompressible flow, has to satisfy this equation right here. Do you remember? Does that ring a bell?
Yes. So I guess the I'm not as comfortable with the that notation, the delta
this one
dot.
right here. Yeah, just this one right here.
So would that be the same as below V would just equal to 0?
Yeah. So we would take each of these components, turn to partial, 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 add them up, equals 0. Hey, we have incompressible flow. So that's how we can show that our flow field is incompressible. If it's not, then what would it be then, Julius? If it does not satisfy this equation right here?
I mean, compressible.
There you go. Yeah, absolutely. So you have a compressible flow field, and then you have to deal with it differently. Okay. So this is one way we understand when we're dealing with incompressible flow, which is very important fluid dynamics. It means that you're working with a flow field where your Mach number is below 0.3. If you're above 0.3 Mach number, means you're dealing with compressible flow. So this is an important distinction to make. And the other approach that we took by using the continuity equation right here was that we could determine, let's say, for example, W, if you know U and V. And because we want...
What number? Oh, I'm sorry, what number did you say? Below 3?
0.3, 0.3.
Okay, for what number? I missed the term that you threw out. I'm sorry.
For the Mach number.
Mach number, okay.
Yeah, which is the ratio of the speed of sound to velocity of your flow field.
Oh, Mach. Okay, thank you.
Yeah. So then the other so we can also use the continuity equation right here. If, let's say, for example, you have a flow field and you need to determine, let's say, for example, if you needed to determine W and you know U and V, we can simply substitute those in there and then just integrate and find out W. And we did a few examples of those in the a few weeks ago. So this is another approach that you can take if you need to determine a velocity component, or you simply need to use the determine if the flow is compressible or incompressible, and it would need to satisfy this equation. All right. So this was the continuity equation. Then from there, we moved on to the linear momentum equation, and we said, hey, we're going to start with F equals ma. And we're simply going to write this side right here in the following way, which was the acceleration term, total acceleration that we dealt with before. And we simply brought the m inside the parentheses. And then from there, we went ahead and for the small fluid packet, we solved for the 3 components of the linear momentum equation, which is this really big equation. And then we said, hey, what about if we're dealing with Newtonian incompressible flow? That means we can actually solve for the Navier-Stokes equation or reach the Navier-Stokes equation. So we did that, and we said, hey, if your normal stresses look something like this, function of pressure, and then your shear stresses look something like this, hey, we can end up with the incompressible Navier-Stokes equation. Okay, which are and then make sure before the exam today that you actually download. I mean, it'll be easier if you download the equation sheet. All the equations that you need are on there. Okay, and then we said, hey, if we're dealing with flow that is inviscid, then that means that these components on this side over here are essentially going to be 0, and we're just left with this other portion of the equations right here. Okay, and then that simply became the Euler equation. So we started with F equals ma applied to a small little fluid packet. we solve for the forces due to normal stresses and shear stresses. Then from there, we said, hey, let's look at Newtonian incompressible flow. So then we ended with these terms right here. And then we substituted them in the equation and we ended up with the Navier-Stokes equation. And then we said, if we have something that it would be inviscid, then these terms over here are gone, and then we end up with the Euler equation. Okay, but we said this equation is actually very difficult, and many times it's impossible to solve. So now, Avery, you have a go ahead, Avery.
Yeah, I just wanted to make sure you can use this equation with compressible flow, right? You just have to take into account that d rho dt.
So if you use with compressible flow, your normal stress term up here, these are going to be a little bit different. These terms up here are going to be, you're going to be dealing with different term up here.
All right. Do we usually just use this equation with incompressible fluids?
This one's for incompressible, yes. For compressible, it looks a little bit different. Not too different, but yeah. And you don't have to worry for this class. Only worry about this one down here. But if you take like aerodynamics or something like that, then you'll have to deal with the compressible form of this equation.
Okay. For the continuity equation, you can use that with the compressible flow.
Yeah, as long as you have the rho inside. Let me go back. As long as you have rho inside the differential, because there actually the density would change with location. It will. So you have to have it inside the differential.
Okay.
Okay. All right. Thank you. And then all right. So then we said this equation is actually very difficult to solve. There's very few situations where you can actually get an exact solution for this set of equations, the Navier-Stokes equation or the linear momentum equation. So we said, hey, let's use dimensional analysis. And this is actually a very powerful tool. And in dimensional analysis, we said, we're going to determine what are the variables that dictate this problem, that are relevant for the problem.
Sorry, excuse me?
Yeah.
So on the previous slide, I had a question. So the thing that I'm confused about is how will we use those equations in the top right in regards to the like all of these lines in the bottom?
Yeah, so these on the top right are already in here. So what happens is you take these terms, these equations here, the linear momentum equation, and these come together, and then you end up with the Navier-Stokes equation down here.
Okay, so like in an actual problem, we would just be plugging in the numbers into the Navier-Stokes equation. We wouldn't have to derive them first and then.
No, yeah, absolutely. Okay. There's a lot of math, not a lot, but some math that goes between the linear momentum equation, these terms, and the Navier-Stokes equation.
Right, and like realistically in a problem, it would be all about what can you cancel out and like all canceling out all these different things, like if it's non-viscous or like if there's no change in gravity or the pressure doesn't change and all that stuff.
Yeah, velocity is a two-dimensional flow field, three-dimensional, all these things. You're absolutely right. And then, and many times then at the end you end up with a very simplified set of equations that you have to solve.
Okay, thanks.
Okay, yeah, absolutely. Okay, I see. Let's see. Gianni, go ahead. You had a question.
Hey, and going back to the Navier-Stokes equations, let's say you want us to find a pressure gradient in the y direction. That means we automatically cross out the other two. We don't have to reference them for anything.
Yeah, as long as you don't have. So it depends. If you have a pressure gradient in the y direction, then that will be there and you have to solve for it. It will mean that your pressure is a function of other variables. We did one example in class that it was only a function of like one direction that we were looking at in that case. So it would depend on the problem where you would have to know, hey, is the pressure a function of just one variable, let's say x, or is it a function of x, y, and z? So it really depends on the problem. How you
perfect. That makes sense. Thank you, Professor.
Yeah, no problem. And so we said, hey, the Navier-Stokes equation is really, really hard to solve. And many times there are no exact solutions. So we said, let's work with dimension analysis. And there's several methods. I'm going to quickly show you the one that was the method that was faster, but more difficult. I suggest that if you feel more with more comfortable with the repeating variables method, go with that one. But there, what we said, hey, we have some sort of problem. The Navier-Stokes equation are going to be unruly to solve for this. We cannot do it. No exact solution. Let's actually use experiments and use the dimensional analysis. And what we said is, hey, we want to figure out what the drag force is. We know it's a function of these independent variables. Then we went ahead and in this case, we eliminated each dimension by multiplication and division. Then we canceled out one by one. So first we said, hey, we want to get rid of the mass. So we got rid of rho. Then we said, hey, we want to get rid of the time. And we knew that velocity had time in it. And then after that, we said, we want to get rid of the length. And then we used the diameter and got rid of it. So this is one method, which I find that, it's faster, but it's a little bit, can be a little more confusing. So if you feel more comfortable with the repeating of variables procedure, please go ahead and do that. That other one is more methodical and is easier to get it. But the whole point at the end, that after going through this analysis, is that you ended up with these universal functions. And universal means that I in my wind tunnel, you in your water channel, I have a sphere of some size, you have another sphere of some size. As long as, and in this case, we're looking at the Reynolds number right here, as long as we're matching the same Reynolds number, the number on the left-hand side is gonna be the same. Okay, so this is why this is extremely important as an engineer, because it decreases significantly the number of experiments that you have to do. And so you would use the Buckingham Pi theorem to do that. Avery, you had a question? Go ahead.
Sorry, real quick. Just do we just divide, like when we get rid of like the rho term, we divide by those units. We get rid of the velocity term, we divide by those units. We just divide the mu by those because we want the Reynolds number, correct?
You're absolutely right. Many times you kind of already know where you want to go.
Right.
So like when you look here at the left-hand side, you're like, all right, I know I want to end up with the Reynolds number. Yeah. And what happens in reality, if you were doing something like this for like your job, let's say, you probably will go through several iterations where you end up with different dimensionless terms. You'd be like, that looks kind of weird. Let me try this other one. And then eventually you end up with something that would look, that will make sense. But in general, like Reynolds number will be like one of those that'll keep popping over and over again. It will pop up again and again. Yeah. So, all right. So, you can use the Buckingham Pi theorem also in the method of repeating variables. And I suggest that one is a lot easier. So, Nicholas, you had a question? Nicholas?
Yeah, when you said like now we eliminate L by dividing by D, how did you get to the D squared on the left side?
Yeah, so so what you want to do on the left hand side is you want to get rid of the number of L's that are on that side. So that's why we squared the D. But on the right hand side, in here it was just one L for length, and here there was only one L.
Okay. All right. Thank you.
Yeah, and it's a good question. This method is a little bit confusing. I just went through it quickly just to remind you guys. But if you feel comfortable with this one, definitely go ahead. It's a lot faster. The other method is more kind of methodical, and it's easier to go through. But either or will work. You'll end up in the same solution. Okay. But what's so powerful about this method is that you end up with something like this curve right here. This is the coefficient of drag for a sphere. And we see here that, as the Reynolds numbers increase, we see that the drag keeps increasing. And that can be a little bit counterintuitive when you think about it. That as Reynolds number goes up, drag is going down. So not a trick question, but what is happening here, Joshua Mayer? What is happening in this region right here where we see that the Reynolds number somewhere like, I don't know, 4 times 10 to the 5 or 3 times 10 to the 5. What is happening there that we suddenly get that drop in coefficient of drag? Do you remember, Joshua?
Is it the boundary layer separation?
Okay, so something's happening to the boundary layer. It's not separating, but it's something's happening to it. So up to this point, you were laminar. Why are we seeing that suddenly drops so quickly? You remember? So it's laminar. So now it's transition to what?
Turbulent.
Yeah. So what we learned is if you have a body like a bluff body, like a sphere, or it could be like a rectangular cross section. For bluff bodies, in general, you want turbulent flow for the boundary layer. If you have a wing,
Right.
no, you want laminar flow for a wing because it's more elongated, and your drag is going to come more from frictional drag due to a boundary layer. But if you have a sphere, it's going to come more from pressure drag, and you want turbulent flow. So that's why we see this drop right here. So let's say something really, really cool. So let me see, Augustus. So something really cool is, all right, Augustus, let's say you're doing experiments and you're running experiments here, a Reynolds number, or you don't even do the experiments. You have this chart and you say, hey, my experiments or the problem that I'm working with, my Reynolds numbers are 10 to the 5 right here, 1 times 10 to the 5. How would you determine the drag force?
I'm not sure off the top of my head.
Okay, so look at this equation right here. You see drag force right here? You see it there, right?
Yeah.
So now I'm telling you 10 to the 5. Now look at this curve. What do you have to do?
You can get the drag coefficient.
Right? So now you have this value right here. So now how can you calculate the drag force?
So you can plug it in and then well, if you know your flow is laminar,
well, you know the Reynolds number. So you already know this. You know all these values, right? In Reynolds number, you know all these variables right there.
Mhm.
So if you know all that, can you determine the drag force?
Yeah.
Yeah, absolutely. You can determine the coefficient of drag too, right?
Mhm.
We go here, you have your experiment, you go up to there, you're like, all right, just go across, figure out what that number is, and now you know your coefficient of drag. And let's say we were close to 0.6. So now if you want to know your drag force, you can calculate that because here that will be 0.6. You have your density, velocity, diameter, all those values came from the Reynolds number. So you can calculate the drag force. Or if you just want to know the coefficient of drag, just draw a line across and you got it. All right. So this is what's so powerful that you don't have to do an experiment. Just by knowing the Reynolds number, you already know what your drag force is going to be. Don't have to do the experiment. This is why we spent quite a bit of time on this so that you understand that if you're doing this type of work at some point, you can easily be able to, in practice, know like, hey, I don't have to do an experiment. I can determine the drag force or coefficient of drag. Wonderful. So, all right, I see a few questions. All right, Jonathan, go ahead.
Yeah, on the last slide when we were doing the Ipsen method,
yep.
Is it possible to do that if we have more than 2 pi terms?
Yeah, you should be able to get the same solution. And if you go back to the slides for that lecture, you end up with like 1 pi term, comma, and then you have like a second term or more, right? Because you have second one, second pi term, third pi term, for whatever, how many pi terms you will have. You at the point that you stop is when you have no more dimensions, right? Where it's dimensionless, everything.
All right, sounds good.
Okay, all right, cool. Tyler, go ahead.
So like when you're trying to calculate FD, don't you have to like triangulate it? So like you choose a Reynolds, you have your Reynolds number and you kind of guess at the drag coefficient, and there's like there were other equations on the sheet where you're like, oh, if the number you get is 1 or greater than 1, then you have to go up and down. But it looks like with this one, you can just calculate it based on that.
Are you thinking about pi flow, trying to determine the friction factor?
Maybe.
Okay, because there you have 3 different variables where you have roughness, Reynolds number, and friction factor. and you're having to go through an iteration because many times you're like, all right, I have no idea what my friction factor is. And actually we'll get to the problem.
Oh,
in
yeah,
a few
okay.
slides. And then you
Yeah.
just guess and you go through the iteration.
Okay,
We'll
thanks.
go through that problem. Now, here, what's really cool about it is you have a sphere, you know your Reynolds number, just go up, go across, and then you know your coefficient of drag.
Yeah, I got those mixed up. Thanks.
Yeah, no problem. And you know what's really cool? If you were given a coefficient of lift, a plot like this, then it would be the same. Are you given drag coefficient for a flat plate or, I don't know, Tonka truck or something? It would be the same. You just go across and find out the drag. So, all right. Devin, you had a question?
Yeah, I just wanted to clarify. You said when you asked about finding the drag force, if you know the Reynolds number, wouldn't you also in this case have to know like the other parameters and not just the Reynolds number?
Yeah, so
to find the drag force and not just the coefficient.
Yeah, so let's what's really cool about this is if the chart, someone has already done it. Let's say this is if it's the first time you're doing the experiment, then you would have to calculate. But let's say someone has already done it and you have a sphere and you know your Reynolds number, then you already have this curve because this is a universal curve. So it doesn't matter if I measure in a wind tunnel, you measure it in a water channel, where you have water, I have air. You have a sphere that's bigger, smaller, doesn't matter. As long as the Reynolds number match, we're going to get the same coefficient of drag. Okay.
Yeah, sorry, I think I just, in this case that you'd have to know the parameters for your Reynolds number.
Yeah.
To like calculate the force.
Yep.
Okay.
Well, you know these, right? You know the density, you know the velocity. You know
right, so I was, assuming if you knew the components of the Reynolds number.
Right. You would have to, knowing the coefficient of drag, you cannot work backwards because some areas here you're gonna have for the same coefficient of drag, it could be different Reynolds numbers.
Right.
But for the Reynolds number, if you know it, then you can know what the coefficient of drag is.
Right, okay.
Okay, all right, awesome. So this is what's so powerful about being able to do this with the, using the coefficient of drag, right? So this is for smooth sphere. If it was rough, it would change. And then we already talked about, hey, why do you have this sudden drop? Transition to turbulence. Bluff bodies, you want a turbulent boundary layer. So let's say, for example, if I asked you, Andrew Keeley, Andrew, let's say I asked you, hey, the Reynolds number of my sphere here is somewhere here. What? And I asked you, is this laminar or turbulent flow here? What would you say?
I would say laminar.
Okay, and I'll ask you, hey, it's out here. What's the flow, laminar or turbulent?
Turbulent.
Yeah, absolutely. So keep in mind that the boundary layer for a little portion is going to be laminar when it starts, but then eventually develops to turbulent. So that's how we characterize it. That even if for a micron or a millimeter at the beginning, even though your boundary layer will be laminar, if it transitions to turbulent, we're going to call this a turbulent flow. If it stays in the laminar regime the whole time, laminar flow. All right, cool. Thank you, Andrew. So then, all right, let's go to the next slide. So we talked about requirements for similarity, and we have these trains. So what's really cool about it is you're an engineer, you're doing experiments, and if these trains are the same geometry and everything as the real life train, then you can actually conduct experiments and be able to understand what's gonna be the behavior of the fluid flow around the real life train. So you have your prototype, you got your model, but we said, hey, you gotta match 3 different similarities. We said geometric, kinematic, and dynamic. A perfect example of dynamic similarity is this one right here, which would be the ratio of inertial forces to viscous stresses. And you know what that is? That's just the Reynolds number. It means that you got to match Reynolds number for your prototype and match that for the model, for both of them. And, or Struhel number, or all the different numbers that we looked at in that day in class. I had a table and all the different dimensionless numbers that we had on there. You have to match them for the 2 problems in order to be able to have a similarity in this flow field. If you do not, and many people, unfortunately, have done this throughout history, you end up with, problems like we saw with the video with the bridge, for example. It's happened with airplanes, happened with different devices that they did not match. And then when you do the experiments in the lab, they don't match real life, and then you get failure. Okay, so these ratios, they're going to be non-dimensional groups. And for two flows, they have to be dynamically similar. So all of the non-dimensional groups must have the same value. So if you have Reynolds number, for your model, has to match for the other, prototype. So let's look at a simple example where this would be, where you can learn about how to work with these numbers. So let's say, for example, you're doing an experiment and you're looking at fish swimming and you're looking at trout, and you find out that trout maintain a constant Struhel number. So this is the Struhel number here. This is your Reynolds number. When you look at this chart, look at the Reynolds number is changing orders of magnitude from 100 to 1,000 to 10,000. And let me try to restart the slideshow to see if it'll let me show the pen, because it's useful to be able to write on the slides. Okay, so share again. Let's see if it'll allow me to write on there. No, just not happy today, PowerPoint. All right, so then, so look here at the Struhel number that over several orders of magnitude in terms of change of the Reynolds number, Struhel number is staying about the same. It's about 0.2, very close to 0.2. So when you have changes in Reynolds number are usual when trying to outswim a predator. So when you have a fish, normally the Reynolds number will go much higher and you get a change in Struhel number. So you're measuring two swimming velocities of fish. You have velocity 1 and you have velocity 2. And then you have for fish that is 0.3 meters long in water, you're given the density, the viscosity of the water, and then you also measure the flapping tail amplitude. And that happens to be, in this case, this much in meters and that much in meters. All right. So the next, you are asked to determine the flapping frequency at the two different swimming conditions. So when we look here at the Struhel number, we have A is going to be the amplitude, U is going to be the velocity, and F is just going to be the frequency. Okay, so if we know the Struhel number, we can easily find out what the frequency is. So let's do that. Let's work on this. So first thing that you should do, and you could imagine you could try to determine coefficient of drag or whatever it is. It's essentially going to be a very similar approach. So first thing you want to do is you want to determine the Reynolds number. And so let's do that for the fish. So we calculate first the Reynolds number, and you have the first velocity, which was 1/4, and you get a Reynolds number of about 84,000. Okay, so somewhere in here. And then we look at the second Reynolds number, and it's going to be about 330,000 or so. All right, about here. So both of them are very close to 0.2. So now you go back and you say, all right, I want to determine what my frequency is. So what I'm going to do is I'm going to choose a Struhel number of about 0.2, and I can determine the flapping frequency. So when you do that, you know your Struhel number is 0.2, and then you simply enter the different values, and you want to determine what the frequency is. You find out it's 2 hertz. Then you do it for the other velocity, and you find out 4 hertz. So this is really, really, really cool to be able to just do an experiment. You don't even have to measure the frequency. Just by looking at Struhel number, you have an idea of what your frequency will be. So this is where this is very, very powerful. And this problem applies to if you have an oscillating antenna in a car, bridge, like we saw the bridge when it was oscillating, buildings when they oscillate with the wind. So this is why using non-dimensional approach is very, very, very powerful. Okay, so now let's transition and talk about internal and external flows. So when we talked about internal and external flows, we talked about, for example, pipes, ducts, and so on. And when we talked a lot about external flows, we talked about like flow over a flat plate, something like this. So first thing here, you have uniform flow. Remember, always, 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 if the flow is uniform, it means every vector is the same length. So if you take the gradient, if you calculate, all right, so what's the gradient of a uniform flow field? Zachary Jordan, what's the gradient? What's the value of the gradient, the velocity gradient of a uniform flow field?
It would just be 0, right?
Absolutely. So this is very important. So then if you have 0 velocity gradient, what does that mean in terms of angular velocity?
There isn't, or it's 0 too.
Yeah, so then you have a rotational flow. And this is what we're seeing in this region right here, where in the internal flow, where is it rotational? But if you go in the boundary layer, it's rotational. So it'll keep growing, 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 and eventually those boundary layers merge, and you end up with a flow field where you have a velocity gradient, where it's changing with position. Now let's look at an external flow. Look at the differences. External flows, you always start with laminar flow. Always laminar boundary layer. Always, 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 always. And eventually it becomes turbulent. Depending on the flow characteristics of your flow out here, it may become turbulent sooner, later. Depending on the roughness of the plate, may become sooner or later, may become turbulent. Or if this is vibrating or something, may become turbulent sooner. But in general, you have this laminar boundary layer where you always start, and then you go to this turbulent boundary layer. And so the flow in here is going to be rotational. Out here, it will be irrotational. Okay. And then, so in here, you're going to have a velocity gradient. Here, you have a velocity gradient. So those are major distinctions between these two type of different flows. So from there, we talked about boundary layer and the shape. And we said, hey, when you have laminar flow, we looked at this velocity gradient right here. And we noticed that the velocity is changing much slower with respect to position in the y direction. So for laminar boundary layers, that slope is very different. And for turbulent flow, it changes very quickly. So then what are going to be the implications in terms of wall shear stress, Kevin Lamb? If you have turbulent flow, and we have that velocity gradient is going to be very high for turbulent flow. So what is the implication for wall shear stress? Kevin? No, Kevin, all right. Alexander Green. So what would it be? What would be the difference, Alexander, for the wall shear stress? If you have that velocity gradient is much larger for turbulent flow, for example. Alexander, Sam, you wanted to answer? Sam? Sam, you wanted to answer or no? All right. Benjamin, you want to answer a question?
Would it be very high?
Yeah, absolutely. So, so you look at the velocity gradient, and we know that our shear stress is going to be a function of that velocity gradient. So then the larger the velocity gradient, the higher the wall shear stress. So that's why everything goes back to what we were talking a minute ago, what we were talking a few minutes ago, is that if you have like a flat plate, you care more about that frictional wall shear stress, because you have your boundary layer. It's essentially what's going to contribute the most amount of drag. Where when you had the sphere, it had to do with a lot with the flow separation. And if it was turbulent, then the flow wouldn't separate. If it's laminar, more likely to separate, drag was higher. If you have a flat plate, it had a lot to do with this velocity gradient. You have larger wall shear stress. So, okay, wonderful. So then, So we said that the UDY, that velocity gradient, much larger for turbulent flow. And then when you look in here, it makes sense. Wall shear stress is going to be larger when you have a larger velocity gradient. All right. So we talked about these equations are in your equation sheet, but essentially, you know, just be familiar with them, know which number goes where, know how to calculate, you know, what each of these mean, how to calculate, you know, boundary layer thickness, momentum thickness, coefficient of friction. Remember coefficient of friction when we talked about it? This was for the coefficient of friction at a point X. If we wanted to know the coefficient of drag, that was a different equation, and that's on your equation sheet. But for knowing the coefficient of friction at a point, this is how you calculate it. Displacement thickness, and then also the shape factor that we talked about. Julius, go ahead.
I know that momentum thickness is that theta term, but I don't really understand still what momentum thickness is, like, and like where it appears on the boundary layer images.
Yeah, so I don't think I have the slide here, but it was, if you go to that lecture, we talked about boundary layer, and we talked about 3 different terms. One of them being how thick the boundary layer thickness is. And we said, hey, boundary layer thickness is up to the point where the velocity at the edge has reached 99% of what the free stream velocity is. So that was the first one. Then the second term we talked about was the displacement thickness. And it was like, all right, I have the boundary layer and it has some sort of shape. Remember, we did the integral of the conservation of mass, and we said, hey, what's coming in, it's uniform flow. What's going out has a velocity profile. What if we make what's also going out to be the flux of mass? Let's make it also uniform. But if we do that, that means that we got to make a gap, a distance, where no flow is going through that. And that gap was your displacement thickness, this delta star here. And then we said that then said, all right, so that was with the conservation of mass. Then we went ahead to the momentum thickness and said, all right, so what is the this momentum deficit that is forming due to the presence of the boundary layer? And essentially we did the same thing where we applied the conservation of a momentum to the flat plate, and we said, hey, momentum going in, momentum going out, and then looking at, you know, whatever that deficit was, which is really the amount of force that is going into the flow that is applying to the plate, was equal to that momentum thickness. And so in general, why is that number used? The reason that is used is many times as people that study boundary layer, boundary layers, to be able to measure the boundary layer is actually very difficult, because we will have to plot it. But the reason is when you have an actual physical probe and getting close to the wall is very hard measuring what's happening at the wall. So that's the main reason why they use this, because this value, if you look at it, it's really large, far away from the wall, and very small near the wall. So your measurements are going to not be as affected as if you were measuring, for example, like the boundary layer thickness. But it comes from this whole concept of what's the amount of force that your flow is applying to the plate. And these are things that are beyond this course. If you wanted to like learn more about it, it'll be like in a viscous flow course or something like that. Okay. All right. Justin, you had a question?
Yeah, will we need to find the distance along the plate where it turns to laminar to turbulent?
So yeah, so that's actually, if you want to know, by definition, we use this critical Reynolds number value of 500,000. In reality, it's actually very difficult to know where it happens, because it could be 510, it could be 499, it could be 495,000, right? But if you're for an exam, it will be 500,000. But in reality, if you can make like a plate really, really, really smooth, then that way you can delay it. But just use like for exam or course or something, use that 500,000 value. That's when you'll get that critical Reynolds number.
Okay, thank you.
Okay. And Julius, I forgot to ask you, did that address your question?
Yes, it did. Thank you.
Okay, awesome. All right, absolutely. All right. So then, all right. So internal flows. All right. So we said we start with the uniform flow, boundary layer, and then it meets at some point the boundary layers from every side. And when it reaches that point, we said the flow is not going to change at all. So once you have that velocity profile, if it's laminar, it's going to stay laminar. If it's turbulent, it'll always stay turbulent, unless you change something, unless you do something to your flow. If it's just the pipe is just staying the same, it's not going to change. And we found that for laminar flow, your average velocity was equal to 1/2 U max. Okay, and then the radial velocity profile looks something like this, that it just changes with little r being the position of the radius and big R being just the radius of the pipe. And it's a parabola. Okay, and then we talked about the this pressure in the flow field. And remember, flow has to follow a pressure gradient. Otherwise, it'll start to decelerate. And if you have no velocity gradient, and at some point it'll stop. So you always need a velocity gradient for flow to move. And this is what this chart is showing you here. At the entrance region is not linear because of the effects of the boundary layers coming together and so on. But once the flow has become fully developed, then from there on, that pressure gradient is going to be linear. Okay, and then there's some equations to find out what that entrance length is when the boundary layers come together and they merge. So from there, if you have laminar flow in a pipe or turbulent, we talked about the slopes, how different they are. And very quickly, if you want to find out what the wall shear stress is, it's just going to be that mu times the strain term, which is down here. And in general, your V is equal to 0 because otherwise you will have VR, otherwise you will have flow coming out of the walls of the pipe. So in general, your flow is just going along the axis. Unless you have some sort of turn or something, then the flow is more complicated. But if you have a straight pipe, your wall shear stress is only going to be a function of that velocity along the axial direction. Okay, and so your wall shear stress is going to look something like this, where it's going to be mu times that velocity gradient. So for turbulent flow, that slope is going to be much larger. So turbulent flow is going to lead to higher wall shear stress, higher losses. So from there, we said, hey, let's go back to the energy equation so that we can actually figure out losses in a pipe. When we did that, we ended up with the energy equation, which had some this correction fraction for the it's like a kinetic energy correction factor. And then we said that alpha, it's going to be, if it's laminar turbulent, you're either going to have 1 or 2. Okay, depending on what the flow field is. Sometimes you have a problem and you don't know if the flow is turbulent or laminar. So if you do not know, you just guess, solve for the problem, you find your velocity, and find out what the Reynolds number is. Then you're like, oh, this is actually really turbulent. The Reynolds number is really high. Then you go back and solve for it again. Okay, so that's how you would address that. And then these other terms, we talked about that these are going to be losses. And then if you have like the head due to a turbine or pump, and the sign just has to do if you're putting work into or getting work out of, and so on. So, all right. So our losses, we talked about major losses and minor losses. The terminology really does not have to do anything with the magnitude. Major has just to do with it's more about the length of the pipe, because when you look at the major term right here, it's going to be your friction factor and the length of the pipe. So you have a really long pipe, it can be, the losses can be very high. But if here in the minor losses are going to be because if you have sudden change in the cross-sectional area of the pipe, or you have a valve, or you have something else installed in the system, then that's going to lead to losses. And then the summation term is just that, let's say you have 5 different pipe segments, so you have to sum them up. And if you have, I don't know, 5 different valves, then you have to sum up the losses due to all the different valves. But when you sum all of these, then those are going to be your losses. Okay, and so the HP is going to be your head increase across a pump. Could be across a turbine that you're generating energy, or you're putting energy into this system. And then remember alpha, if it's 1, and again, this is in the equation sheet, but just so that we talk about it. If it goes 1, turbulent, 2, it's laminar. So in the case, and this is for a special case, if you have a horizontal pipe, constant diameter, and if it's constant diameter, that means that your velocity of 0.1 is going to equal the velocity of 0.2, as long as it's fully developed, right? So we have that your velocity is going to be equal if the area is not changing. Your alphas are not going to be changing, because what we said with pipe flow, once it's fully developed, it's not going to change. It's not going to become laminar or turbulent. It won't. It's once it's there, unless you change something in your system. So when you do that, when we know that about the system, then this equation up here simply reduces to this. Why? Because you can see how you can cross the Z terms right here. You can see how your velocities are going to be the same. Your alphas are going to be the same. So those terms are going to cross out. And then you just have the pressure drop, which is how pressure is decreasing with respect to this thing. Eric, go ahead.
So based on this, does that mean that a pump and a turbine in the same steady incompressible flow would cancel each other out?
If you had like a pump and a turbine in the same system, you mean?
Yeah, because in the energy equation, it's HT minus HP, and HP and HT are the same.
No, so it would be like, so in a pump, you're putting in work. So let's say, for example, you're, I don't know, you're trying to drive flow across inside a pipe. So you would have a pump that is turning, and you're putting energy through electricity or something, and you're moving the flow. And the turbine, what it's doing is, many times you have like a reservoir, and with gravity is making this turbine turn, and from there, then you're making electricity, and turning kinetic energy into like electrical energy. So normally you would not have both of them in the same system.
I see. Okay.
Okay.
All right. Thank you.
Yeah, absolutely. No problem. Thanks for the question. So then, so then it will reduce the energy equation. It will reduce to the following. And then there was a separate analysis that we conducted using dimensional analysis, and there where we ended up was here with this following equation. So these two come from different analyses. This one came from dimensional analysis. This equation right here is simply a simplification of the energy equation. Okay, so this came from dimensional analysis, where we said, hey, the drop of in pressure inside a pipe is due to like friction, length, diameter, density, and then you go through, using Buckingham pi theory and so on, and then end up with your pi terms. So that's where this came from. But what was done many years ago is that these two were equated, and then we end up with our Moody chart. And then our Moody chart, let's quickly go through this just in case you haven't. And this is essentially the Moody chart comes from like the friction factor. This comes from the Colebrook equation. And for the, Avery, go ahead. You have a question?
Yeah. On the previous slide, was the V denoting volume or velocity?
Should be velocity, average velocity. Yeah.
Okay, cool.
Yeah, no problem.
That's all.
Yeah. And yeah, many times you'll see, like when you see like 1/2 rho V squared, that's like the dynamic pressure term. So you many times will see that one So, okay, all right. So then, so this one, these curves come from the Colebrook equation, and Colebrook, you can either use the Colebrook equation or the Moody chart. Sometimes you use the Moody chart for an initial guess and then go back to the Colebrook equation. But let's say, for example, you have pipe flow and you have some Reynolds number. I'll make up a Reynolds number like about 1 million. And then your pipe has some roughness. I don't know, let's say 0.004. So we go here and find at 1 million, that's roughness. And then if I just go all the way across, that means that this value right here is going to be my friction factor. Okay, so now I have the F value, and then I could go back. Let me go back to this previous slide, and then I could enter that value in here, and I know what my pressure drop is going to be. Okay, so it's very powerful to know how to use this chart. Benjamin, you had a question?
Yeah, can you go back to that chart for a sec?
Yeah.
So on the right, you had that roughness factor. And with the pointer, you went directly horizontally across from where the intersection between that and the Reynolds number is. You do that. If you do that, then what does the Reynolds number matter?
No, because what you're trying to find out is where they intersect, where the Reynolds number intersects with that curve.
Okay, yeah, I do get it now.
So, but if you go lower in Reynolds number, then you gotta go higher up, because that curve, you see, if I go over here, then I have to keep climbing up.
Okay, I do understand. It just took me a sec.
Yeah, no worries. Good question. And actually, following up on your question, everyone, please pay attention that over here, this is relative roughness. So it's not the actual absolute roughness. It is relative roughness. So it's a dimensionless parameter. And in this case, it has been non-dimensionalized by D, which is the diameter of the pipe. So just keep that in mind. All right, so make sure you know how to use the Moody chart. It's very powerful, or the Colebrook equation. Actually, it would be good to know how to use both. So for the then to find out the KL values, the losses, you have a chart like this, and you're like, all right, I have a bend, and my bend is 90 degrees, and I'm using, I don't know, it's a long radius or short radius or something. And then you go in here and you get the different KL values. And then you substitute it into this equation up here. You can find out the head loss due to the minor losses. All right. So, okay, so let's go through this example. And let's say we have a pipe and you want to determine the pressure at 0.1. Okay, so you have your 0.1 right here. And then first we're gonna look at the problem if there are no losses. And then the second problem if there are losses, okay? So flow going from left to right, making all these turns and then coming out over here. So then, okay, so let's start with the problem. So, we're going to use the energy equation to determine the pressure at 0.1. Okay, and so we start with the energy equation. We want to find out pressure 1. So here's pressure 2. So Attica, what's going to be the pressure at 0.2? Attica. No Attica. Okay. You wanted to answer the question?
Yeah, I'm assuming it would be 0 P atmospheric at the end of the faucet.
So not 0, it'll be P atmospheric.
Okay.
Yep. And then unless you were dealing with gauge pressure, then yeah, you would say 0. But in general, it's easier if you just absolute pressure. But you're absolutely right.
Okay.
So then yep. So we have atmospheric pressure at the exit. So then we can enter it in here. Then Z, how do we determine Z? Well, let's just go through all these segments. So we have L2, then we have L4, and we're going to sum those to see what was that height difference. And then we will determine, we should know the velocity. So let's go ahead and start dealing with the problem. So let's first assume that there are no losses to solve this problem. Okay, so let's first state the assumption. So just as you just stated, pressure at point 2 is going to be atmospheric. Then we have, that water density, then the viscosity, the dynamic viscosity for the water, and then we know that our velocity is just going to be the flow rate divided by the area. Okay. So since there are no losses, all these terms are going to be equal to 0. No turbine, no pumps, no losses. So all those are equal to 0. So then we can go into the energy equation. We can cross these terms out and then move all these terms from this side to the other side. Okay. And we have alpha 1 and alpha 2. If it's turbulent, you enter 1. Laminar, you enter 2. Depending on the Reynolds number. Again, if you don't know the Reynolds number, just guess 1. And if you have to do something like this in the exam, just say, hey, I'm going to guess that my Reynolds number is going to be laminar, and just put alpha is going to equal this value. Okay. So so as I just said it, if you don't know the Reynolds number, can be determined and just guess a value for alpha, and then we iterate. So we go ahead, we end up with the following equation. Why do I have the Q in here? Just in case you were given the flow rate. So instead of the velocity. So this is how you would calculate your velocity. And then from there, Z2 minus Z1 is, as we stated, it's just going to be that height difference. That is going to be L2 plus L4, which is going to be this term right here. All right. So this is how we will solve the problem. So in this case, you have to be given a number for like the cross-sectional area and the flow rate and the lengths, but you can, quite easily determine that. But what about if we have to include the losses? So let's look at that case. If we have the losses, same approach, but now we have the head losses. We're going to have those due to the total length of the pipe, and then those due to the different connections and elbows and so on. So when we do that, some of the major losses, minor losses, all the major losses are going to be here, which is going to be the total length of the pipe, and then all these other K losses. Okay, and then we can put all of them in here in parentheses, and then multiply by this term, which is going to be the same for all of them, and then we go back to this equation, and that's how we find pressure 1 at point 1. So if the flow is fully developed at point 1, we know that your average velocity, this mean velocity, is going to be the same as V1. And then we know that all these lengths are going to be the same. Not the same, but the L is going to be this summation right here. But then the next question will be, how do we determine our friction factor, right? Because that's the one variable right here that we don't know. So how do we determine that? We go to the Moody diagram or the Colebrook. So let's finish the class by going through the, Tyler, you had a question.
Yeah, so I didn't quite understand what I'm supposed to do if I don't have a Reynolds number. And you said plug it in and stuff.
Yeah, so you just guess for a value for alpha. Okay, so let me go back to the previous slide. And PowerPoint's not behaving well today, so give me one moment. Let me see. Okay, there we go. So in here, so your alpha, it's either going to be 1 or 2, depending if it's laminar or turbulent. If you don't know the Reynolds number, just guess. You can enter 1, make your life easier, 2, whichever. And then you solve for the problem. And then that's in the case that you don't know the velocity. Of course, if you know the velocity, then immediately you determine the you would determine the Reynolds number. But if you don't know the velocity, then you would just guess a value, go through the problem, find out the velocity, calculate the Reynolds number, and then if your guess was wrong, then you go back and calculate again.
And so how do you know if your guess is wrong?
Based on the Reynolds number. So what's a critical Reynolds number for pipe flow, for internal flow?
So are these the numbers where based on if it's laminar or turbulent and all that, or?
Right.
Okay, I don't know it off the top of my head, but.
So before today at 7 o'clock, 4,000 above, turbulent, 2,100 below, laminar. Okay, just know that number, and it's a good number to know as an engineer. It's good to know that if you're somewhere 2,000 something, 3,000, you're going to be transitioning to turbulent flow. Okay. So so that's how you would determine.
Professor, I'm sorry. In a problem, would you set it up so it's well below 2100 or well over 4000, so there's no confusion, or would there be a possibility that it would be in that little middle range?
If it's in the middle range, it's very hard because all of you get unique numbers, and I try to play with different numbers. But if by any chance you end up with the transitional number, just enter in there. This is a transitional number, and there's no alpha for a transitional number. If it was, I'm going to assume from here on that it's turbulent laminar, whichever you prefer, just to solve the problem to show that I know how to do this.
Awesome. Thank you, Professor.
I tried to make it, but everyone has a different Spire ID number. If that problem is in there, I don't remember if there's this type of flow, but type of problem. But if there is, that's how you would approach it. Okay.
Awesome. Thank you.
Yeah, absolutely. No problem. All right. So then let's finish off with an example where we actually can do this and work on this. So let's say you have oil flows through a 100-meter long pipe, 30 centimeters in diameter, and it has a head loss of 8 meters. Okay, so they gave you HL. And then the density is the following. The viscosity you have, so that's one thing to make sure you understand, that difference between kinematic and dynamic. They're different quantities, okay? So you don't make a mistake when you're calculating your Reynolds number. So here we were given kinematic, which already has density included in there. And then this is the relative roughness. And you're asked to determine the average velocity and flow rate. So this will be a perfect example where you have to guess because you don't know the velocity from the beginning. So let's start first, and we're gonna guess, we have to guess a friction factor, okay? So we're going to guess that for, if you go to the Moody chart, you look where this curve is, for 0.002, and that's the curve that we're going to be working with, right? That curve will do something like this. And so you can guess some friction factor value. If you're really wrong, it means that when your approximations at the beginning are going to be very wrong. If not, you're going to be close. All right. So for me, I guess something close to wholly completely turbulent, which the friction factor is equal to 0.0015. That's what I guess. I don't know. I have no idea. So now I'll go to the Darcy-Weisbach equation, which is the head loss for, and just because we only have major losses, right? So we have head loss equals our friction factor, L over D. Those values were given here, L over D. We don't know the velocity. That's what we want to determine. And 2G, of course, we know. And we were given the head loss. So we rewrite it such that on one side we have friction factor, which we don't know, but we're guessing, and then velocity that we need to determine at the end. And these numbers just come from these others that we've calculated. All right, so we're gonna guess. So we'll do that first. So I guess friction factor to be 0.015. So when we do that, I enter that into this equation, take the square root, and then I can find a velocity. And I get this value for the velocity. So then I calculate a Reynolds number, it gives me an 84,000. So I take that 84,000 and go to the either a Colebrook equation or the Moody diagram, go to 84,000, and now I can find my friction factor, right? I draw a line and I go all the way to the end and find out what my friction factor is. So when I do that, and I wish we had a board so I could show you, but the computer's not gonna let me show you two screens. So I could show you what I'm doing on the Moody diagram. But then with this Reynolds number, I found that the friction factor is 0.196. So it's actually not that far. So with that value, I go back to this equation, calculate the velocity, get 4.9, not that far, and calculate new Reynolds number, about 74,000. Good, all right, I wasn't that far off. And then I do that again. And when I do that, go to this Reynolds number on the Moody chart, look for the friction factor. I get back 0.0201. So you see now I'm getting very close. I'm going through iterations, I'm getting closer. Calculate the velocity. Hey, this is actually very close to this. Calculate the new Reynolds number, 72,000. So you see how I'm slowly approaching the Reynolds number. And then we do it once more, and once more. It's just like, all right, that's pretty much the same number. Find out the velocity, very close to that number. That's the actual Reynolds number. So once I have that, I'm really happy. I'm very close to the number. So I said, hey, that velocity was the actual velocity. I plug it into my flow rate, and I can calculate the flow rate because that's the quantity we wanted to do. So in the last 2 minutes, I'll show you the same thing. Instead of doing the Moody chart, let's do it using the Colebrook equation. So in the Colebrook equation, we go through the same process. This is a Colebrook equation. We guess a friction factor. So we have this equation here. And first, we guess a friction factor that we enter here. And when we guess that friction factor, we were able to calculate a velocity. And then with that velocity, we were able to calculate Reynolds number. So now let's calculate that quantity. This quantity has to equal 1. If it's not 1, it means we're wrong. So we do that, right? We guess 0.015. We got this velocity, got this Reynolds number. The right side of the equation must equal 1, but what we find out actually equals 0.87. So we're off. So we're like, all right, that means that we need to change our friction factor to come closer to this side of the equation to be 1. So again, let's, and you can use with the equation or use the Moody diagram to guide you, but now you're gonna have a new Reynolds number that you can calculate with this new velocity. So you have this new Reynolds number, which is 84,000. You're gonna get a value that looks something like this. The velocity you calculated, your new Reynolds number, plug it into the Colebrook equation, right? We plug in here Reynolds number. We plug in here this new friction factor, and we get now that we're 0.988. Hey, that's closer to 1. Still not equal, but closer to 1. Avery, you have a question?
Yeah, I was wondering, like, I mean, I guess this is only on the previous slide, what the Reynolds number that we're trying to get was, because didn't we like know when to stop, like when you got a certain Reynolds number?
Not by Reynolds number. You'll see it in a moment, but now what I'm seeing is I want this number to come close to 1. In the previous one, what we saw is just the Reynolds number started to asymptote to some value.
Okay.
Here we're gonna see the same thing. We're gonna see the same effect in a moment. Yeah. And Nicholas, you had a question?
Yeah, so I pretty much had the same question about last slide. Did we just kind of stop once we kind of got to that Reynolds number where it was like barely changing?
Yeah, yeah.
Okay.
Yeah, it was barely changing. But if you want to be like for sure, then you do it with the Colebrook equation. But essentially, you'll see you end up in the same place. Yeah. But so we'll keep guessing. So now we know it's 0.988. And we're like, oh, this is great. So you see, we went from 0.015, which is the first friction factor we guessed, and we went up to 0.0196. So it means that we need to keep going up, but a tiny bit. So and then you're guiding yourself with the Moody chart because you're kind of going along. And then so the next one with this new Reynolds number that we just calculated, that 73,000. We go to the chart and we get that the friction factor is this, 0.0201. Find out what the velocity is, and we get the Reynolds number. So you see that the Reynolds numbers are they're going towards an asymptote, some value. So now we have this new Reynolds number. We can plug it into the Colebrook equation with this new friction factor that we just found, and we're now at 0.999. I mean, that's really close. And then we can do it once more, and you're at 0.99996. I mean, at this point, you're pretty much there. But this is how you would do it. With the Colebrook, of course, you're going to get more exact values. With the Moody chart, it's not a linear plot, so you're kind of trying to approximate it as much as you can. But this is how you would do it if you have to iterate. All right. So tonight, depending on which group you are, 6 o'clock, 7 o'clock, and then there are different Zoom meeting IDs. So either myself or the TAs will be in one of those. I suggest don't waste time trying to look up on the internet problems that are similar to it. I make up my own problems. So everything we talked about, and then use the equation sheet. And make sure you print the cover page. Turn it in. The reason why turn it in will not let you upload it is because it does not identify like typed letters. So make sure to type to print the letter, or you don't have to print it, but just submit it as part of your PDF file. And then one last thing, last time people were working after the hour when the exams were done. And that's not fair because some folks, finished when they were supposed to. So we said, all right, this time you have to be done. You only have 10 minutes to submit. And if you're late, you're gonna lose points. Just to make it fair for everyone. That's all we want, to make it equal for everyone. So if you have questions, I'll hang around for a few minutes. Otherwise, I'll see some of you this evening.
Professor, we meet again tomorrow, right?
And we meet again tomorrow, so we get
Okay.
double
Just
dose.
wanted to make sure.
Yeah, we get double dose of back to back, but then you get a longer break. So
Can we meet Wednesday too?
no, not Wednesday. It's something because today's Patriots Day, something like that. So
I think it's because it was Wellness Wednesday, wasn't it?
is it something like that? I know normally when Patriots Day happens,